Hello, my dear students, and welcome back. So good to see you all again. Today, we're going to tackle a chapter that feels, well, it feels like pure magic. But I promise you, by the end of this little session, you'll be the magician. Let's get right into it. Electromagnetic induction.
Okay, I know. Exams are so close, right? And this chapter, I've been seeing your comments in DMs. It's giving a lot of you some tension. Hana, I get it.
But listen, don't you worry at all. That is exactly why I am here, Beta. Together, we're going to break this whole thing down and make it super, super simple. You just watch.
So, are you ready for the first magic trick? I'm going to show you how the brilliant Michael Faraday discovered a way to create electricity, poof, out of thin air. Well, almost. Think about it. No cells, no batteries, just a magnet and a simple coil of wire. How cool is that? Let's begin.
All right, for our first act, let's see this magic in action. How can a simple magnet actually create an electric current? Pay close attention to the setup on your screen.
So, look here. We have a coil of wire, right? And it's connected to this thing called a galvanometer, which is really just a fancy current detector. Now, watch what happens. When we push the north pole of this magnet towards the coil, look, the needle moves. We've made a current. It's magic. But now, if I stop the magnet, see, the current is gone. Nothing. Now, if I pull the magnet away, whoa, the needle moves again, but this time in the other direction.
So what is the secret here? What's the trick? It's one simple word, change. It's not the magnet itself, Beta. It's the motion. The magnetic field going through that coil has to be changing. No change, no current. And get this, the faster you move it, the faster the change. And guess what? You get more current. It's as simple as that.
Okay, so we've seen the magic trick. Now it's time to learn the secret behind it, right? The law that makes it all work. And this is where the genius Michael Faraday enters the picture.
So, first things first, we need to understand a simple concept. It's called magnetic flux. Now, don't let the name scare you. Just imagine magnetic field lines are like raindrops, and the area of your coil is like an open bucket. Magnetic flux is just a measure of how many raindrops, or field lines, are passing through your bucket. More lines going through? That's more flux. Simple.
And, of course, this is physics, so there's a formula. But don't worry, it's a very friendly one. This flux, we call it phi b, it just depends on three little things. First, how strong the magnetic field is, that's B. Second, the area of our coil, that's A. And finally, the angle at which the field lines are hitting the coil. We use cos theta for that. So the formula is just B times A times cos theta. See? That's all.
And now for the main event, Faraday's law of induction. Beta, listen to me. This is so important for your exam, okay? Put a star next to this. The law is beautiful in its simplicity. It says that the voltage, or what we call EMF, is created only when the magnetic flux through the coil changes. And the amount of voltage you get depends on how fast that flux is changing. A quick change gives you a big voltage. A slow change, a small voltage. That's the heart of it all.
Okay, great. So we know we can make a current. But which way does it go? Clockwise? Anti-clockwise? To answer that, we need to learn about our next secret rule from a physicist named Lenz. Think of him as the opposer.
You know, this is a super common question they'll ask you in the exam. Faraday's law tells us how much EMF we get, but Lenz's law, that tells us the direction. So let's solve this mystery. Is it clockwise or anti-clockwise? Let's find out.
Lenz's law is actually pretty funny when you think about it. Just imagine the coil is really stubborn, okay? It hates change. So when you try to push a north pole towards it, the flux increases, right? The coil says, no way, get away from me. And to push it away, what does it do? It creates its own north pole on that side to repel your magnet. And as you know, to make a north pole, the current has to flow anti-clockwise. See? It always fights the change.
So that's the formal definition you see on the screen. And you know what this is really about? It's about the law of conservation of energy. Physics doesn't give you a free lunch. You can't get energy for nothing. You have to do work to push that magnet against the coil's repulsion, and it's that work, your effort, that gets converted into the electrical energy. Makes sense, right?
Okay, so we've established that changing the flux creates a current, and we did that by moving the magnet. But what if we flip it? What if we keep the magnet still and move the wire instead? Let's see what happens.
Well, this gives us something called motional EMF. It's so cool.
If you just take a simple wire, a conductor of length L, and you move it with a velocity v through a magnetic field B, you generate a voltage just by moving a wire. And the formula? Oh, you're going to love this one. It's just BLV. That's it. EMF equals B times L times V. So easy to remember.
All right, theory is great, but let's practice, okay? Let's solve a typical exam problem. This is exactly the kind of question you could see. We've got a square loop, some numbers for its size and resistance, a magnetic field, and the field changes. Let's find the EMF and current. Now, don't get scared by the numbers. We'll do this together, step by simple step. Look at this. It's just 4 simple steps. Step 1, find the initial flux. We have the formula for that, right? B times A. Step 2, what's the final flux? Well, the problem says the field drops to 0, so the final flux is 0. Easy. Step 3, calculate the change in flux and divide it by the time given. That, my friends, is Faraday's law, and that gives you the EMF. And finally, step 4, we use our old friend Ohm's law, I equals V over R, to find the current. See? You totally got this. It's just a method.
So, we've learned the theory, we've learned the laws, we even solved the problem. But you might be thinking, okay, but why does this matter? What's the big deal? Well, let me show you the grand finale. Because this little magic trick we've been talking about, it literally powers our entire world.
Take a look at this machine. This is an AC generator, and every single thing in your house, the lights, the fan, your phone charger, the TV you watch your Instagram reels on, all of it is powered by a giant version of this. And how does it work? On the exact same magic we just learned, electromagnetic induction.
The idea is just brilliant. Instead of moving a magnet back and forth, which is tiring, right? You just take a coil of wire and rotate it inside a magnetic field. Just spin it around. As it spins, the flux passing through it is constantly changing, going from maximum to 0 to maximum again. And what does a changing flux create? A changing voltage. And that's what we call alternating current, or AC.
Whew, we've covered a lot. So before we finish, let's put everything important in one place for your final revision. Get your phones ready. You're going to want to take a screenshot of this.
And here it is, your ultimate cheat sheet for this chapter. We've got magnetic flux, BA cos theta. We've got the king of them all, Faraday's law. EMF is minus N times the rate of change of flux. That minus sign? That's Lenz's law, reminding us that the current always opposes the change. Then the super easy motional EMF, bluff. And finally, the AC generator, which shows how rotating a coil gives us that beautiful alternating current. Seriously, take a screenshot of this right now. This is your key to getting full marks on this topic.
And just like that, the magic trick is revealed. You are now a magician of electromagnetic induction. You know the secrets, you know the laws. It's not so bad, is it? I told you! Now believe in yourself, Beta, practice a few more problems from the book, and you are going to absolutely ace that exam. You've got this. All the very best.